Experiments often provide more powerful evidence than other observational processes, but experiments can also fail. In this lecture, I'll discuss different kinds of errors in the design of experiments that destroy or at least hamper their evidential power. Let me start with correcting a widespread misunderstanding. There is a group of so-called failed experiments that aren't really failures at all, because the experimental design does not contain any grave errors. Perhaps the best example of these is the famous Michelson-Morley experiments performed in 1887. Its goal was measuring the difference between the speed of light traveling in different directions. Michelson and Morley expected such a difference because they, like most other scientists at the time, believed that a vacuum in space was filled with a substance that allowed light waves to pass through it. This was called the luminiferous ether theory. They designed a very clever and well-controlled experiment. Nevertheless, it is often considered the most famous failed experiment because Michelson and Morley, against their expectations, could not detect any relevant difference between the speeds. They thus failed to do what they intended to do. However, it was exactly because the quality of the experiment was so high that it stood up against their expectations and the dominant theoretical view. The Michelson-Morley experiment, rather than being a failure, turned out to be very productive by providing the first strong evidence against ether theory. Many so-called failed experiments are actually productive in this way. Learning when an expected effect does not occur, as Edison observed, is often as important as learning when it does occur. However, not all experimental failures are productive in this sense. There are experimental observations from which we cannot conclude anything of interest. If the experimental process is not designed correctly, so that the assumptions made explicit, for example, in Mill's method of difference, are not satisfied, then we cannot justify acceptance or rejection of a hypothesis with those experimental observations. The most important errors in the experimental design concern the lack of control of the relevant causal factors. These errors can arise in many different ways. Let's have a look at some prominent examples. The Flemish alchemist van Helmont investigated what made plants grow. For this purpose, he planted a small willow sapling in a vat with soil of a specific weight. He let the tree grow, giving it only water, and after 5 years, weighed both soil and tree again. While the soil had not changed in weight, the tree had grown more than 30-fold. As van Helmont had observed the addition of water as the only difference, he concluded that the mass gain of the tree was produced by the water. Today, we of course know that this conclusion is false. Most of the mass of a tree comes from the air, more specifically the carbon dioxide it processes via photosynthesis. Helmont could have found out about this if he had controlled the supply of carbon dioxide. But he did not have the technology to do so, and more importantly, he did not even consider it as a relevant causal factor. At his time, most scientists took air for a static substance that could not turn into solids, like wood. So, he drew the wrong conclusions about his hypothesis because he failed to control for an important background factor. That's a very common experimental error, as we often do not know what the causally relevant factors are even today. Another kind of error arises when experimenters fail to control factors that arise from or with observation. The so-called observer effect describes how the act of observing itself might have an effect on the target variable, for example, when the temperature in a liquid is affected by the heat flowing from the inserted thermometer. The confirmation bias describes psychological effects on a person reading off the measurements. For example, if the person knows which samples have been intervened on and expects that the intervention produces a strong effect, then there often is a detectable tendency to read off larger effects from these samples than from those not intervened on. Unless one controls for this bias, the experimental observation will not justify any relevant conclusion. In experiments with humans or animals, problems also arise from additional effects from the intervention. Placebo effects, for example, arise when the patients believe in the effectiveness of the treatment intervention makes a difference. They might show as a lessening of symptoms, even if they are given a pill that the patients believe will cure them, although this pill does not contain any causally active substance. To control for this, modern drug studies always assign some patients without their knowledge to a control group where they receive such inactive placebo pills. When dividing samples into treatment and control group, selection bias is another kind of error that threatens. Inadvertently, one's selection might be influenced by the very factors that have an influence on the target variable. A famous example comes from World War II. The Royal Air Force tried to minimize bomber loss from enemy fire and therefore investigated the damage of all returning aircraft. Pattern can be seen here. They recommended adding armor to those areas that showed the most damage. In contrast, mathematician Abraham Wald argued that one must not exclude those aircraft that did not return from their mission. Those were the ones, he said, that sustained fatal damage and therefore did not return. The ones that did return showed damage that was not fatal. Assuming that damage is uniformly distributed across aircraft, armor therefore should be added to areas that were not damaged in returning aircraft. To summarize, these examples of experimental errors, as well as many others, compromise the process of experimentation. Those processes fail to control for background variables, or they intervene not only on the target variable, but also on some other factors, or they fail to correctly observe what is to be observed. Only if we manage to avoid such errors can the observations justify the conclusion. In other words, only then do we say that the conclusions from the experiment are internally valid. But how can we know whether our experiments include errors? We have two general strategies here. First, we should apply all available knowledge when designing experiments. This includes theoretical knowledge, for example, about the composition of air, about heat flowing from bodies, including measurement instruments, and so on. This is the content of every scientist's theoretical training. However, this strategy also includes tacit experimentis knowledge, things that are learned from experience and working in a lab, but that many people might have a hard time expressing explicitly. Which liquid to use for chemical extraction, at what temperature, are often more dependent on the experienced laboratorian's intuitions than on knowledge of theories. And so are questions of how best to clean your laboratory equipment. Experimenting is very much also a craft. But this means that avoiding experimental error isn't merely an issue of finding the right theoretical knowledge. It also requires practicing a lot with people who have experimental experience. The second strategy of detecting errors starts with the fact that many hypotheses scientists are interested in already have been tested experimentally before. In those cases, we can look at those experiments and learn from them. We do that by repeating those previous experiments. Now, not all experiments are repeatable. Only if enough information is available about the setting, the intervention, the control, and the instruments used can we say that an experiment is repeatable. We then might have different reasons to repeat an experiment. One goal is to reproduce the previously reported results. If a repetition yields the same result, then we can be more confident that it did not contain errors. If, however, the result cannot be reproduced, this indicates that the previous or your own experiment contains an error and you can start searching for it. Another reason for repeating an experiment, this time with slight variation, is to see how dependent the result was on the previous experiment setup. For example, you might repeat a chemical reaction between two liquids, but now at a different temperature than in the original experiment. We call such processes replication. If you fail to replicate an experiment in this way, then you learn that certain factors, like for example temperature, have a causal impact on the experiment result. These are ways how to find out about experimental errors, in particular failures of controlling causally relevant factors. Once you learned about them, you can then proceed to correct the error by performing various strategies of control.